I'm going to give you just in this half hour, for those of you who don't know about FileBench, a little brief tutorial, very brief, and then I'll talk about some of the new features that have been added to it in the last year and a half, for those of you who may be familiar with the older FileBench and wondering what all I've been doing with my time. And my boss is in the back of the room, so I also want to make sure he knows what I'm doing with my time. So there are many, many ways that people try to test file systems. Actually, dozens of different things. Some range from essentially very simple tests, do reads and writes and things like that, to much more complicated things. They either don't really stress the file systems correctly, or they take an awful lot of effort to set up. And if you think of the file system or the benchmarking space, there are the micro benchmarks on one end that do very simple, repetitive things, which can completely miss some of the performance advantages of your system or misrepresent them. There are the complicated ones that are actually based on real applications, which, particularly if it's the application you're using, can be very good, but can be very expensive and time-consuming to set up. And then kind of in the middle is ones that run based on models of the applications. What FileBench is one that allows you to do any different model you want. You write it in a special modeling language, which I'll talk about briefly, and then you replay it through the FileBench benchmark. And this allows you to emulate a whole lot of different applications and run them very quickly on your system. So in particular, Sun was concerned about getting an up-to-date file server benchmark that would be similar, that would capture the way file servers are used these days as opposed to the way they were used about 20 years ago. So there was a performance engineer at Sun named Richard McDougall, who was very involved in database performance, and he started the FileBench project a number of years ago, came up with the idea of the workload modeling language, and developed it as open source in SourceForge, along with some other Sun engineers and some people out in the SourceForge community. It had a burst of development, and then Richard went off to work on other things at Sun, and it kind of stalled. And when I came into the picture, the ZFS and the Fishworks folks had decided that they would really like to use FileBench extensively, and they would like to have it integrated into Open Solaris, which by now there was such a thing as Open Solaris, so it could still be in the open source community, but within Solaris, where it would be forced by the Solaris people to come up to Solaris standards of quality and cleanly code and everything, and force us to clean it up. So we spent a lot of time cleaning it up in order to get it ready for this and bring it up to the Solaris standards. Put it into Solaris in 2007, and then continued working on it. Some of the stuff since then is listed here, and I guess, come to think of it, you're not going to understand what they are until I get to the next slide, so never mind. But we are working on, one of the more important things is we're working on an NFS version 3 client so that we can have common client across multiple architectures and operating systems. So the basic principle of FileBench is that it's a model-based application emulation. It's highly configurable architecture that you can add these modules to, such as an NFS client. The models are expressed by the workload modeling language, which is called .f, not .fff. Sorry about that. Which confuses, .f confuses some of your editors into thinking it's Fortran, but it is actually not Fortran. This consists of high-level flow operations, which schedule I/O activity or block waiting for other activities to happen within the system, or even just consume CPU resources if you wish to do that. It has a hierarchy of processes and threads, exactly like Unix and Solaris. And a really novel feature is Filesets, which allow you to create hundreds of thousands of files in an object called a fileset. And these can be created in such a way that they mimic real file systems. We can use things such as a gamma distribution to set up the sizes and depths of the tree that's produced by this. So that's very handy. One of the last of the sort of marketing slides here on FileBench. So one of the things that Richard did, as I mentioned, he was into databases. He actually traced real database systems running using, I'm not sure whether dtrace existed yet, but he used a number of tracing techniques to trace them, see what they were doing within the threads and what the I/O was being produced, and use that to tune a model, which we do give away as part of FileBench suite of online transactions processing. Now you can adjust the number of, now we've got this model, you can adjust the number of threads, the number of worker processes, that kind of thing, I/O rates, to scale it to whatever size system you want to keep whatever size number of disk drives you want busy in whatever file system. So right now, it's generally, the way it's built, it mainly tests local file systems. You can, of course, export it over NFS by mounting an NFS drive. But then you do have some of the variation due to the client, in which we want to get rid of in the future. This is kind of the rough architecture. All these different model languages. These are .f files that have been written for it. You can run them then on this framework that it interprets that. We have a POSIX client, essentially, plug-in, and an NFS v3 is well along in development. Although the guy that's working on it is only part-time, but he's working on it very hard. So I think we'll have that pretty soon. And down the road, we'd like to have NFS version 4 and sys as plug-ins. So as I said, it's basically mimics real operating systems. You can declare processes. Processes can have multiple threads. You can have multiple threads executing the same workflow. You can have multiple threads with different workflows. It's all how you describe it in the language. And you can have threads and processes block on each other through synchronization operations. And this is a very flexible synchronization operation that allows you to not only keeps one from getting ahead of the other, it actually keeps this one from getting too far ahead of that one, and that's all adjustable. So you'll see how that's used when we get to the OLTP benchmark in a bit. The way we picture this is flow states. You'd go to these two IOs here, perhaps issued essentially simultaneously by having them be asynchronous IOs. They join up. User busy, if you are actually running on the server, say an application server, you can actually set some CPU utilization to chew up server time, so it's not just the file system that's using it, and see how things work when you do that. And it's another I/O. And you might have another process over here doing similar things, and they're synchronized together with the synchronization flow ops. Here's just a few examples of the kinds of flow ops that we support. It's a very long list now and growing. Your basic read and write, create a file, delete a file, append to a file. And you can now make and delete directories, read directories. The semaphore is the very flexible blocking system that I was mentioning. There's also a couple different ways of limiting things by rates and by throughputs. And all of these things are parameterizable with attributes, exact attributes depending on the particular flow op. So you can, of course, adjust the I/O size. There's some adjustment of what type of I/O pattern. As I said, we use probabilities in a number of places, and you can adjust aspects of the probabilities. You can adjust all sorts of things about the file sets, and et cetera. Again, nice long list of very flexible stuff. And this can be adjusted both by sort of statically within the .f language statement, or there are ways of doing it from the command line or from a scripting program on top of that, and I'll get into that in a moment. So the file sets are one of the first cute things that I discovered in FileBench when I started working on it. They're a fractal tree of files. And the original version uses a gamma distribution to set this up. You can select size, depth with the directories, and it will automatically populate all this. You can say whether they've initially got data in them or not. If you don't want something that fancy, you can tell it the depth of 1 and just have one big flat directory as well. You can have uniform sizes of files. You can, again, use gamma distribution to select the sizes of files, so you can get a big variety of them. And particularly good for mimicking file servers with this sort of thing. And files used to be a separate object in FileBench. One of the first things I did after taking over was convert this so it's really just a shorthand for a file set with one file in it. So your old programs still work, but by doing this, all flow ops that reference files and file sets can reference each other, whereas before it was kind of certain files, certain flow ops could be used with files, and certain other ones could be used with file sets. Now everything can be used with everything. It doesn't care. You don't notice that under the cover there's really a file set with one file being created. Just to give you an example of what I'm talking about with the .f language, this is a very simple .f language file here. We're defining a file, which name of large file 1. This is the path will be set later on to tell you exactly where it is. It starts out defaulting to /temp because we've set up a variable called $dir to /temp. But once you've loaded this in, you can change it from the command console to be pointing to something else. And there's also, as I said, a script that can run multiples of these and change this each time it runs it. This is, again, a variable that's telling it what the file size is, defaulting to 1 megabyte, but again, can be changed. This is saying that you want the file pre-allocated. If it's already there from the last run, you don't want to pre-allocate it. You want to just reuse it. And the parallel actually doesn't make any sense here because we've only got one file. But if you were doing a file set with lots of files, this will cause it to spawn multiple threads and try to allocate the files in parallel, which is nice if you have multiple processor cores. Speed things up a bit, or multiple disk drives. And we define a single process here, which we called random read. One of them, we define a thread called random read thread. Memory size is specifying an I/O buffer size, basically, within each of these threads. Instances, it's defaulting to just one thread, but you could say 16 threads, 24 threads, whatever. Each one would get its own 5 megabyte space. And then this very simple one, a flow op, called a read flow op. It's set to random over here, and then it's doing IOs of IO size of 8K, which is what it's set for. And then we're limiting the rate at which this is done with the event limit flow op. If you've set the event limit, turned on event limits, this will actually set default to one cycle through here, I believe every second. And you can set that to do faster ones. So that's the basic scheme of a .f workload, the most simple one. You can make compositions of processes and threads, much more complicated ones than this. If you do run that particular one, and you get this sort of output coming out, this is running it through the script that I mentioned before. This is the way we think people should normally run FileBench, although you can run the basic C program as well. So it started out as a C program, and to add some extra features to it to allow you to run multiple different tests with different types of parameters, we have a script language which are called .profile, .prof files, and those will call individual workload files and then adjust their parameters. So you can run lots of different random reads of different sizes from that. Each one will spit out stuff like this when it gets done. We see the number of IOPS per second and so on. In this particular case, we didn't set a limit, so it's actually running as fast as possible. And it will summarize these statistics and store them off in an HTML file that you can actually look at than from a web browser to see what results you got, and with some pretty tables. And there are some other hooks for doing other statistics out of this. This is sort of the same program again. I mentioned running it from a script. This is the script that was running it. It said that to run it for 60 seconds, but still using /temp for everything. That's the name that gets attached to it. And random read is the name of the .f file that was getting brought in. But we've changed the file size. We changed the I/O size here before we actually run it with those variables that I mentioned. If you are running just a basic C program, which is now called Go FileBench, and you invoke that directly, it does let you interactively change stuff around. And it actually has command line finishing stuff built into it too, typing ahead stuff. We produced quite a few workloads. So quite a few were done by the original team. Most of these are somewhat more intended as examples of how to do it than necessarily well-tuned ones, except for OLTP, which actually has been carefully vetted against a real database system. The others, it's on our list to vet them, but they're not bad. Most of them are fairly close. I've added video server workload more recently to it. And then the file macro and file micro are the names of two canned profiles that are included. And you run file macro or file micro, it just does this whole list in order and gives you the entire results. It runs systems I tested on, which are somewhat old servers, runs about a half hour to an hour each of these sets of tests, and gives you lots of nice data that you can compare and see if, well, in my case, if things I've done to FileBench have changed the performance, but other people do it to see if their file systems actually change the performance and make sure everything's still working. Just to give you an idea of how to use this more complicated structure for a database, here we have the database server application that's included. We have a bunch of 200 user processes by default, which are randomly reading out of the lookup database tables. There's 10 writers that are writing into the database tables. And then there's one log process that's logging. And the semaphore synchronization is used so that to keep these sort of in lockstep. And in particular, let's see. I think for every 200 reads, we do a log, and for every I think this is set for something like every 10 writes we do a log. I forget exactly. I'd have to look at the code. That's all tunable, so you can do it, make it match whatever files database server or database system you're interested in. This is the kind of output you get from it, showing breakdown by different flow ops, and then a summary of the actual IOPS that were generated, megabytes per second transferred, and that kind of good stuff. Here's the part I'm most interested in, because this is stuff I've been working on for the last year or so. The variables I mentioned before are ones that you statically set. In simulation, it's kind of nice to have sources of random variables. So we've created a random variable, which every time you access it, it produces a different number from a random distribution, which you set up previously. You can specify uniform, gamma, or you can set up a table of base distribution. That's all I've got built in at the moment. And it will spin the random number generator and run it through the distribution and give you the appropriate number back. Another thing that I felt was necessary for more complicated workloads was something similar to inline subroutines. We call them composite flow ops. You have define a flow op just like a thread, but now it gets called by other flow ops as though it were a flow op itself, and that gets added dynamically as you're reading the program in, and that way you can have much more elaborate systems without having to write quite as many flow ops down. And there's been a lot of call for multi-client support, especially when we get into network stuff. we'd like to hook this in with one of the several frameworks that are around for doing multi-client operations. We haven't quite got there yet. We're evaluating it. This is a little kludgier, but it does work. The FileBench script gets some extra information added to it. It goes off and runs clients on the other machines, targets them all to the same server, and collects and compresses the output back and feeds it to you. So it does work. We'd like to get it hooked into something like Faben at Sun that's a multi-client benchmark. As I said, there's a little more work to do to get it there. Another thing that was missing before was if you had a file set, the way they were stored internally, you basically were getting them round robin when you asked for them and cycling through that way. And I wanted to be able to randomly access them. So we actually use an AVL tree inside now to do it. And I can randomly access files. I can specify whether they are existing on the disk or not. It's made it much more efficient, particularly when in that particular scenario. And the even cleverer thing, I can use a random variable to supply the index, and then I can have any sort of distribution of access, hot files versus not hot files that I want out of that. So that's fairly recently been put back in. The other thing is in getting preparation for the file system clients, I've put in some hooks to make it easier to add the file system client support. And I got a couple people ask me for video server workloads. So there is an example video server workload now. In the past, Sun's used FileBench quite a bit for various things, such as NFS protocol checking. They've done a lot of stuff on ZFS to see how to improve it. And some papers out there about those things, which you can look up. In the future, as I said before, we want to get more support for networks with clients in there. We also want to get a better framework, multi-client frameworking benchmark. There's a lot of bugs I'm still working on to fix, although it's gotten a lot more stable, thankfully, in the last year and a half. And a few little features here and there that I've realized I want, or people like you have asked me for, that are on the queue to go in. Lots of Bugster bugs on it. We're working away on that. I'm on this full time, and also happy to answer questions over email